Okay, so here we will introduce two theorems for deriving the differential form of the Maxwell equation. So the first one is called the divergence theorem, or you can call it Gauss theorem. So based on the name, you can imagine this is applying for the Gauss law. Okay, so actually what is divergence theorem? The divergence theorem actually looks like this. Okay, for a F is a vector field. Okay, it should always satisfy this equation. Okay, looks very horrible. What does it mean? Okay, so on the left side, it is a surface integral for a closed surface. A surface integral for a closed surface. So this is somehow we are familiar with. This is for the Gauss law on the left hand side. We have a integration of the E dot dA. Okay, so actually this is for that one. Okay, we just need to change F to E or F to B. Okay, so that we can apply this one for for the Gauss law. Okay, on the right side, we also have this triple integral for the dV. Triple integral for the dV, but for the inside part, it is not a vector. It is actually this is a gradient dot F. Okay, gradient dotted with this vector field, or the divergence of a vector field. The divergence of a vector field, okay, I forgot to mention. For the divergence, okay, this is a vector field. This is a vector field. Okay, so the divergence operator will change this vector field into a scalar field. Okay, this is a scalar field. Okay, we don't see any vector sign there. So it turns out to be a vector field, a scalar field, sorry. This is a scalar field. Okay, but for the curl, okay, this is a vector field. Okay, we take the curl operator. Okay, so the answer, this one is still a vector. So this is still a vector field. A vector field. Okay, just keep this small thing in your mind. Okay, so this is a scalar field. Okay, so we try to integrate a scalar field into integrate the scalar field, okay, over the volume. It's just like integrating the density over the volume. Okay, so this is also a scalar field. This is also a scalar field, which means that we try to consider this is a small dV, and then we try to consider for every part we try to calculate the divergence of F. The divergence of F for every single volume, and then we try to add them together. So it turns out to be a triple integral. Okay, so it is actually like this. Okay, so it looks horrible. What is it? What does it mean? Okay, so on the left side, it is a triple integral. This is triple integral. This is a triple integral. This is double integral. This is triple integral. Okay, but for the divergence, it is something like so. This is a double integral, triple integral. This is a divergence. It looks like one derivative. Derivative. Okay, derivative. One derivative. Okay, because you can see here. The divergence, okay, this is a derivative, although this is a partial derivative, but it is still a derivative. Okay, so you can see this is a derivative, so it just looks like we have one derivative to cancel with our integration. So it looks like it is actually not only look like, it is actually a form of the fundamental theorem of calculus. Fundamental theorem of calculus. Of course, in the calculus class, you only learn something like if you have let's say f prime of x equals f of x and then it is actually if and only if integration of f of x dx from a to b equals f of b minus f of a. Okay, so you take the antiderivative. This is the antiderivative, and then you plug in the lower and upper bound. Okay, so this is the fundamental theorem of calculus in one dimension. Okay, so this is fundamental theorem of calculus in three dimension. Okay, so this is a triple integral. You still use something like a derivative to cancel one of the integration, but you really need this divergence operator. Okay, you need this divergence operator. Okay, so it says that surface integral of a vector field over the boundary of the volume equals the volume integration of a divergence. So what does it mean? Okay, so it is like this is a surface integral. This is a surface integral, and this is a divergence over the whole volume. So it is like for every part, you can see. Let's say maybe I draw it here. Okay, so yeah, so the divergence look like you can see it is something like pointing inside or pointing outside, and then with it adjacent, it is also like pointing inside or pointing outside. So for the adjacent part, it will be looking like this is pointing to that side, this is pointing to that side. Okay, so for the adjacent part, they will cancel each other until for the boundary part, okay, only pointing the outside part will remain. Okay, so finally it turns out to be this one. Looks like for every part you have a dA, and then you can see whether this part the vector field is pointing inside or outside, and then you try to sum of them together. Okay, so we will make use of this divergence. Okay, so actually for the divergence of the inner part, okay, the adjacent volume will cancel each other, so that only the surface remain. Okay, this is a interpretation. Yeah, in words. But if you would like to find a rigorous proof, you can try to check out this link. Okay, you can see the proof of the divergence theorem, and later also the Stokes theorem. Okay, so yeah. So if you have interest, you can check it out. But this is not a calculus class. I will not try to go through the proof. Okay, and the next one is called the Stokes theorem. Okay, so Stokes theorem. Okay, it says if we have a vector field f, okay, it will satisfy this equation. On the left side, we are still familiar with it is a line integral for a closed loop or for an Ampere loop. Okay, so we can apply it for Faraday's law and Ampere's law on the left side. Okay, on the right side, it actually looks like a double integral. Okay, actually a surface integral. Surface integral, but it is not for a closed surface. It is only for an open surface. And inside part, it is actually the curl of f. Okay, so this is still a vector field. Okay, so a vector field dotted with this dA, and then you try to integrate it. Okay, so it turns out to be a scalar. This is also a scalar. So this is a line integral. Okay, so yeah, so you can see this is like a single integral. This is a double integral. This is a double integral. Okay, for the curl, you still have some partial derivative here. So you can still consider it is a first derivative. Okay, so it's still, you use a first derivative to cancel one of the integration. Okay, it becomes a single integration. So it is also the fundamental of theorem of calculus in two dimensions. Okay, so it says the line integral of a vector field over the boundary of a surface equal the surface integral of a curl of the vector field over the surface. Okay, so the physical meaning is something like, or if it is the contour. Okay, so actually you try to calculate the, let's say this is ds, okay, and then you have a vector field, let's say f. Okay, so you calculate all the f dot ds over this one. Okay, but actually it is something like you try to calculate the curl for the f, which means that you try to calculate or how it try to rotate, So for the adjacent node, okay, so they should something like continuous. Okay, so which means that for this point, okay, you try to integrate like this. For this point, you try to integrate like this. So actually, for the adjacent loop, they will just cancel each other until for the boundary. If it is rotate like this, okay, it has no one to cancel with it. Okay, we don't consider the outside part. Okay, so the remaining one is only the boundary. Okay, so actually it is just like when you try to calculate the curl of the vector field for a surface, and then for all the inner part, they will cancel each other. The only remaining thing is only the boundary. It turns out to be a single integral or a line integral. Okay, so similarly, I don't try to go through the proof. If you have interest, you can check it out. Yeah, but actually there's an interesting story about the Stokes theorem. Actually, actually it is like the 19th century, 19th世纪18几年了。Okay, so Stokes when he tried to invent the Stokes theorem, okay. Of course, at that time, it cannot distribute very quickly like nowadays. Nowadays, if you have find some new thing, you can just publish a paper, and then everyone in the world, if you can access the internet or access the journal, then you can read that one. At that time, it is not that convenient. Okay, so at that time, when Stokes invented this theorem, he tried to make it an exam problem. So very, very tough. Okay, make the proof of the Stokes theorem to be an exam problem, like an entrance exam or whatever exam. I don't really remember. You can just try to Google it, and then you can find that exam paper actually. Yeah. So yeah, you try to make it an exam paper. Of course, this is very difficult because he has spent many times to really discover this Stokes theorem, and then if you give it as an exam problem, okay, you just give the student limited time to really prove it. Yeah, actually the result is only one student can really prove the Stokes theorem in the exam. The one is called Maxwell. Okay, it's actually the Maxwell for the Maxwell equation. So actually later on, Maxwell used this Stokes theorem to really derive the differential form of the Maxwell equation, or the Maxwell equation. So this is an interesting story. So given the divergence theorem and the Stokes theorem, we can try to derive the differential form for the Maxwell equation. So first of all, we start from the Gauss law. Okay, so just now we already mentioned that for the Gauss law, originally it looks like this, but we try to change this Q to be a triple integral of the charge density. Okay, this is the charge density. Okay, so using the divergence theorem, the left side, this is the triple integral, becomes the divergence, and then you take the triple integral for the divergence of E. Okay, and then so which means that this one is equal to this one, and this one is actually this one. So which means that this one, okay, this triple integral equals this triple integral. Okay, so we can write it like this one. Okay, like this. Okay, so this is a triple integral, and then we try to actually put this one inside. So it turns out to be rho over epsilon naught, rho over epsilon naught. And actually, this triple integral is true for arbitrary volume. For arbitrary volume, originally you cannot simply cancel this one with this one, and it is not correct. But if this equation is true for arbitrary volume, then you can really cancel it. Yeah, because you can just try to change it a little bit, then and then you can find for all the small volume they should be the same thing. So finally, you can really cancel the integration sign to make the integrand itself equal to each other. So finally, we have this divergence of E equals rho over epsilon naught. Okay, so it turns out to be the differential form of the Gauss law. And similarly, you can also have divergence of B equals 0. Okay, all the steps are the same, except on the right side is all the way 0. Okay, so we have simply derived the differential form for the two Gauss laws using the divergence theorem or using the Gauss theorem. Okay, next is the Faraday's law. So for the Faraday's law, okay, originally it looks like this. Okay, this is E dot ds for the closed loop or for the Amperean loop. On the right side it is negative d dt, and then this is phi b. Phi b is a double integral of the b field. Okay, so using the Stokes theorem, on the left side it is a line integral. So on the right side, we take the double integral or the surface integral for the curl of E. Okay, so which means that this one is this one. Okay, and this one equals this one. So actually, this one equals the upper one. So we put this one here, put this one here. And then we also try to put this differential derivative into the integration sign. Of course, for rigorous mathematics, they will consider you need to prove whether it converge 是不是收敛. But actually, yes, at least for physics guy or for engineering guy, we are not that rigorous. So we try to assume that this is convergence. Okay, this one and this one should be the same for most of the cases, unless you try to create some strange situation. Otherwise, usually these two will be the same thing. Okay, so we try to believe putting this one inside the integration side will be the same. But we need to care about, okay, this is the original derivative. Okay, after putting in, it should become a partial derivative, because after the integration, it becomes a scalar. It only related to the t. But for this one, if you put inside here, so b is actually the function of x, y, z, and also t. Okay, these are four variable function. Okay, so you need to use the partial derivative rather than the original derivative or the ordinary derivative. Okay, so actually you can see this is the double integral. This is the surface integral. This is also the surface integral for the same area, and similar to the previous argument, we can just cancel the integration sign, because this surface integral is true for arbitrary surface. So which means that the integrand should be the same. So finally, we have this curl of E equals negative partial b partial t. Okay, so this is for the Faraday's law. And finally, we can also derive it for the Ampere's law. For the Ampere's law, it looks like this. This is the integration of b dot ds, and then this is mu 0 I enclosed. We try to write this I as a double integral of the current density. This is the current density, and then plus epsilon naught. Okay, this is the d phi e dt. So the whole term is actually the displacement current. But here, phi e, write it as a double integral of E field. Okay, so similarly, for the left side, we can use the Stokes theorem. Okay, so this is the line integral of B dot ds, and then the right side will be the surface integral of the curl of B. Okay, so which means that this one is this one, and then this one equals to this one, so this one equals to that one. Okay, so we'll put this one here, put that one there. Okay, of course we try to distribute this mu 0 into here, this mu 0 into here. Also this epsilon naught, put it inside. Also we try to put this one inside so that the original derivative becomes a partial derivative. Okay, so the right hand side look like mu 0j, and then epsilon naught, mu 0 epsilon naught, partial e partial t. Okay, we just put everything inside, and then we try to make it a big integration. Okay, so still, okay, these two surface integral is for the same area, and then for arbitrary area they are the same. So the integrand should be equal to each other, which means that we have a curl of B equals mu 0j plus epsilon naught partial e partial t. Okay, so we finally derive the differential form for the Ampere's law. Okay, so it looks very complicated. But actually it's just a symbol. So finally we can derive the differential form from the integration form like this. So of course in the textbook we only it only mentioned the integration form, but actually differential form might be could be useful. Actually for this one can be useful for something like the fluid dynamic or something. Yeah. Okay, so finally I will also mention the conservation of charge. The conservation of charge look like, oh, you cannot create a charge, you cannot diminish a charge. So yeah, actually we can really write out the conservation of charge as an equation like this. Okay, so actually the conservation charge, why it is looking like this? Okay, so let's see how we can write it out. Okay, so first, rho is the charge density over the space or over a volume, over the volume. Okay, and then J is the current density. Suppose we assume there is a cold surface. Okay, so actually we can try to define the current. The current will be the surface integral of the current density. But here we put a negative sign. Which means that if it is going in, the current is positive. If it is, let me see. Yeah, if it is going in, then the current is positive, because for this double integral we always define dA to be pointing out, outside. Okay, so if J is also pointing outside, then this double integral is positive, and then we put a negative sign, which means that if J is going inside, I will be positive. Okay, so so actually using the divergence theorem, this is a surface integral, so it can be turning into a triple integral, but we have the divergence of J. Of course we have a negative sign, so we just put it in. Okay, so I is actually taking this form. Okay, so next we have this I equals dq dt. And yeah, actually if Q is changing, it means that we have I. Okay, so here we try to consider what is the Q here? What is the Q here? Okay, so suppose the Q is changing, and if I is also going in, then it will accumulate the charge inside this volume. So that's why we put a negative sign here, so that it matches this I equals dq dt for this case. Okay, so I equals dq dt. And then so Q is actually triple integral of the charge density over the volume. Okay, so it looks like this. And then we also try to put this one inside. So it becomes a partial derivative. Okay, so here, this is a triple integral. This is a triple integral for the same volume. And then they equal each other. So that according to the, similar to the previous interpretation, which means that this equation is true for arbitrary volume, which means that the integrand itself should be the same. So finally, we have this integrand equal to this integrand. So we have partial rho partial t equals, we have a partial rho partial t equals negative divergence of j. And then we try to move it to the left side. Okay, so it should be this one. Okay, this is a gradient, this is a vector, so we should have a dot in between. Okay, so we should have a dot in between, which means that it should be like okay, divergence of j. Okay, so this is actually the conservation of charge. Okay, so so we can see how the charge conservation is compatible to the Maxwell equation. Okay, so we need some other equation. Okay, so actually originally this one okay, or maybe I try to write it out. Okay, for the Ampere's law, it is something like curl of B is actually mu naught J, and then or maybe plus epsilon naught partial E partial T, something like this. Okay. So this is the static current, this is the displacement current. Okay, just now I mentioned whether we need to add the third term, fourth term, so on and so forth to make it even more correct. Okay, so now it is like this. So we try to take divergence on both sides. Okay, take divergence on both sides. So on the left side, it becomes divergence of curl of B. Okay, it becomes a scalar. Okay, on the right side, you also try to take the divergence. Okay, so take the divergence to the first term. This is a scalar, so we can just put it out. So this divergence directly go to here. So we have divergence of J. And then for here, we also try to consider, okay, mu naught epsilon naught are constant. Okay, originally, this divergence is outside this partial derivative, but we also assume that, okay, we can exchange the order of the derivative. So we put this one really inside. Okay, so it turns out to be like this. And actually, we have this so-called the divergence of curl is 0. You can check it on the Wikipedia. We have this one. Or if you don't believe, you can try to verify it by yourself. You can try to use the definition of the curl, the divergence of the curl, or at least you already have the expression of the curl, and then you try to take the divergence. You can see that it should be 0. It will turn out some second derivative term. Okay, if you try to take the curl, okay, you can try to take the curl of this one. Okay, take the curl of this one. So in that case, we will have something like a partial x partial y, and then partial x partial c, and then finally it turns out to be 3 pair, and then all these 3 pair will cancel each other, and then finally turns out to be 0. Okay, you can just use the definition to really derive it. It is pretty easy. Okay, so in this case, we have this divergence of curl is always a 0. Okay, so which means that this one is 0. So which means that yeah, this one is 0, and then here divergence of E according to the Gauss law, divergence of E is rho over epsilon naught. So we can put this one into there. Okay, so putting 0 into here, we have 0, and then equals mu naught, and then divergence of J putting here, and then epsilon naught partial T, and then with this one. Okay, so actually this one is like epsilon naught partial T, and then we put this one here, so it becomes rho over epsilon naught. So epsilon naught is a constant. This epsilon naught can be putting out, so it will cancel with this epsilon naught. Okay, so finally it turns out to be a partial rho partial T. Okay, so which means that, okay, we can see this part is actually the conservation of charge. The conservation of charge is like this: partial rho partial T plus divergence of J is 0. So this is 0 according to the conservation of charge. Conservation of charge. Okay, so this is a 0. So it turns out to be 0 equals 0, or yeah, or maybe you can just cancel this one. This is not 0, so you can just cancel it. So it turns out that you can really derive the conservation of charge out. Okay, so actually both of them are okay. So it tells you that it is correct, or this Ampere's law is compatible with the charge conservation of charge, or charge conservation. So which means that we don't really want to add even more terms to the Ampere's law to make it even more correct, because at this moment it already satisfies the conservation of charge. If you add more terms, then it will possibly violate the conservation of charge, which is not good, because we will always consider conservation of charge is correct. Okay, as we have mentioned in chapter 21. Okay, so I think we have pretty much gone through. We have pretty much